In this talk, we introduce a counterexample to the stability of a pruning of the medial axis called the burnt medial axis, which seem to be experimentally stable under small perturbations to the input manifold. We structure our exposition in the following way. We begin with an introduction to the classical medial axis and its inherent instability, continue with proposed prunings via the burnt and lambda medial axis and other methods, and finally introduce our counterexample, which is based on Bing's house. We begin with the definition of the medial axis. Let M be a manifold in Rn. We define the medial axis of M to be the set of points in Rn with a non-unique minimum distance to M. Note that these points could be located either inside or outside of M. Typically in applications, only the interior medial axis is considered useful, and the notation abused accordingly to denote only the interior medial axis of M as its medial axis. We shall follow the standard abusive notation for the rest of this talk. We can begin to construct the medial axis in 3D by looking at balls which touch two or more faces of the set, which in this case is the cube. We begin with the sphere in the center of the cube, which touches all 6 faces at once. Then along each diagonal we have a family of spheres which touch 3 faces simultaneously. Then there is the set of spheres which hit only 2 faces at a time, and these fill out a sheet which links adjacent pairs of diagonals. Altogether, this forms the medial axis of the cube. An alternative characterization of the medial axis that may be easier to visualize is Bloom's grass fire method. You can imagine lighting a grass fire along the boundary of the input shape and burning the fire inwards at a constant rate. The medial axis emerges when fire fronts meet each other. A useful feature of the medial axis is that it captures both topological and geometric information. As proved by Leutier, the medial axis captures a homotopy type of the input shape. Furthermore, if you bend or stretch the input shape, the medial axis will bend and stretch with it. This makes the medial axis a useful tool in shape recognition, and its famous introduction by Bloom in the 1960s had this application in mind, in particular as a tool for differentiating clusters of cells in biomedical imaging. Several other authors besides Bloom have introduced the medial axis under other names and for other applications. The earliest known introduction was that of Federer in 1959, but he is not often given credit due to the dense and often incomprehensible nature of his writing. The medial axis provides a descriptor which is useful in many contexts, from differentiating classes of cells in biomedical imaging to providing a framework from which to produce animations in computer graphics. Such a skeleton is also useful for tasks like surface reconstruction and complex model simplification. As such, it has been an object of constant study over the last 50 years. Unfortunately, one limiting factor in the use of the medial axis of a smooth manifold is that it is not necessarily topologically stable under small perturbations of the manifold. As can be seen here, small bumps in the input manifold lead to large spikes in the medial axis. This is a chronic problem in a skeleton used primarily for shape recognition, as shapes which look the same modulo some slight imperfections arising from noise or sampling irregularity can lead to wildly different medial axes. In order to address this instability, several methods have been devised to simplify the medial axis. These include the object angle of Atelier and associates, the lambda medial axis of Chazal and Leutier, which we use in our computation, and the erosion thickness of Jan and colleagues. Perhaps the most widely used of these methods is the lambda medial axis, which we define as the circumradius of the set of points found by the closest point projection on the original set. By varying the parameter lambda, we obtain different prunings of the medial axis, which eliminates some of the noise incurred from perturbations of the input set. Different values of lambda are useful for different applications, but lambda must be larger than the size of the sampling radius and much smaller than the distance between the medial axis and the original set, also called the reach. This guarantees that the lambda medial axis preserves the homotopy type of the set. However, for the rest of this presentation, we focus on the burning method, introduced by Jan and colleagues, which generalizes Bloom's original grass fire analogy. In 2D, we illustrate this by taking the interior of a closed curve as input. We then imagine lighting fires at the extremities of the set and letting them burn at a constant speed until multiple fire fronts meet, forming the medial axis, which is generically a topological tree. Then we continue burning the medial axis itself from its leaves. When we reach the node of the tree, the fire pauses until both fire fronts reach the node. Finally, the medial axis is burnt away to a single point, maintaining the homotopy type of the set. This generalizes to 3D in the obvious way. Some definitions are necessary before we proceed further. We define a p-dimensional simplex, denoted p-simplex, as a convex hull of p plus 1 affinely independent points in Rn. A collection of simplices K is called a simplicial complex if it follows a few simple rules. 1. Sigma being an element of K implies that all faces of sigma are also in K. 2. Sigma and tau both being elements of K implies that sigma intersects tau is a face of both sigma and of tau, including the case that the intersection is empty. We then say that K is closed under face relation and that K is a simplicial complex. Next, we define the notions of collapsibility and contractibility. Let K be a simplicial complex, and suppose there is a pair of simplices sigma and tau of K, such that sigma is of dimension p take 1 and tau is of dimension p. And furthermore, sigma is a face of tau, and sigma has no other cofaces. Then K minus the free pair sigma tau is a simplicial complex called an elementary collapse of K. We say that K is collapsible if we can perform a sequence of elementary collapses on K until eventually K is reduced to a single point. We say that a space is collapsible if there is a triangulation of the space that is collapsible, where a triangulation is a simplicial complex that is homeomorphic to the original space. On the other hand, a topological space X is contractible if it can be continuously strung to a point. Note that all collapsible spaces are contractible, but not the other way around. Perhaps the most famous contractible but not collapsible object is called Bing's house, and it forms the crux of our counterexample. Here we illustrate Bing's house for the unfamiliar viewer. It consists of a hollow cube forming the house with two rooms, an upper room and a lower room. From one room you cannot access the other room, but both rooms have access to the outside world via corridors. Just as Santa Claus jumps down the chimney to bring Christmas presents, you can jump down or up a corridor into Bing's house to access the interior. The two corridors are connected to the walls of the house with a flap each, which comes as an artifact of the construction of Bing's house as a deformation retraction from the closed ball, which we animate here. The house begins as a solid cube into which we dig two corridors, one downwards from the roof and one upwards from the floor. Once the corridors have reached a sufficient length, we begin expanding them to form a top and bottom room. The expansion continues until each room wraps around the other room's corridor. Finally, when the expanding rooms meet themselves at a pinch point behind the corridors and also meet each other at their roofs and the ball's boundary at the remaining room faces, the house becomes entirely two-dimensional. This final house is not collapsible because it has no boundary where a collapsing sequence could begin. We again perform this isotopy, but we now compute an approximation of the medial axis of the cube as it's deforming. The medial axis begins as a collection of sheets bisecting pairs of walls of the cube, and it is both a contractible and collapsible object. As we deform the cube, its medial axis deforms as well. In our isotopy from the cube to Bing's house, we stop at the fattened Bing's house, which is just short of the point at which the deforming cube becomes entirely two-dimensional, so that the medial axis inside of the deforming cube will be itself Bing's house. We focus here on the exact moment when fronts from the medial axis wrapping around the corridor meet. In this instant, the fronts interrupt where the collapsing sequence from the boundary would be, causing the medial axis to become the non-collapsible Bing's house. Therefore, the medial axis would burn to Bing's house rather than burning to a point as it used to, although the deformation was smooth throughout. Therefore, we have found a counterexample to the burned medial axis being stable. From this we conclude that stability of a medial axis simplified using a collapsing scheme is not always possible. Note that although we animate the growth of the corridors symmetrically, the transition can be made generic. In particular, this means that the transition from a collapsible to non-collapsible medial axis is not the result of a symmetric configuration. The topological behavior of singularities under such generic transitions has been studied by Kimia and colleagues. To better understand the type of transition which causes the medial axis to go from collapsible to non-collapsible, we present an example of the same type of transition, but in a slightly simpler setting that is more easily illustrated. We consider a local deformation of Bing's house near a flap. We call this deformation collapsibility via exposure. We begin by pressing inwards on the wall, splitting the flap in two, eventually exposing the corridor. Until the point at which the corridor is fully exposed, the topology remains essentially the same. At the final moment of this transition, we fully expose the corridor, and now Bing's house is free to collapse. To begin with, the part of the corridor where the flap used to be now has a free boundary, namely the edge. From this edge, we can collapse downwards along the corridor, and then the floor of the top room, where the flap used to be attached. We then can collapse all the walls and the floor of the bottom room. Next we can collapse the other flap, the corridor going to the top room, and finally the top room itself. In summary, we've discussed the medial axis and its shortcomings. We've also discussed some potential fixes for these shortcomings. In particular, the lambda medial axis, which we use for our computations, and the burn medial axis, which we've shown to be unstable even under generic perturbations. We demonstrated this through the deformation of the cube into Bing's house, which causes the medial axis to suddenly go from collapsible to non-collapsible. With this, we thank you for your time and welcome inquiries via discussions or emails.